In Lesson 7, we're going to be talking about induction and deduction, logic, the contrapositive, and converse and inverse. And all of these things are basically logic related, and usually in a traditional geometry course, these topics are covered in that course, not usually in algebra. But the interesting thing is that logic applies to all of mathematics, not just geometry. The Greeks, and primarily Euclid, are said to have found logic. Euclid is sometimes called the father of logic. Let's take that one step further, though. God made Euclid and made all of us, so God is really the true father of logic and father of everything. He's the creator of everything. He knows how our minds are designed to work, so he knows they're designed to analyze things using deductive reasoning, inductive reasoning, and analogy. That's how he's created us. Let's take a look at inductive reasoning and deductive reasoning in Part A here. Inductive reasoning, that's basically the process of finding a rule. And how do we find a rule? How do we discover a rule? Well, usually we do that by observation, by making some kind of observation. The scientific method, that is an inductive reasoning process. So let's just write that down. You should write this chart that I have on the board on your paper. The scientific method. Science, the definition of science is observations of God's world or observations of the physical world. If we observe something and we see that repeated over and over and over again, we have found a new rule in God's creation. Deduction, that's the process of using a rule. And a good example of that is Euclid's postulates, which we'll talk about in another lesson. Euclid's postulates or rules, he's got 10 of those, and those are used to find new truths. How do you think he came up with those 10 postulates? Well, those were arrived at by induction, by observing the physical world. So in mathematics, the basis of it all is inductive reasoning, observation of the physical world. Now, if we observe the physical world incorrectly, then our rules are wrong, and that means our deductive reasoning about them would be wrong as well. And a lot of times it is. The only true rules that we can trust are biblical commands. And one more type of reasoning they don't talk about in Lesson 7 is an analogy, and a word problem is a good example of an analogy, because a lot of times what we do there is we take the words and we make a comparison or a similar statement just in algebraic terms, in terms of an equation. We turn the words into an algebraic equation, and that helps us solve the problem. Our word problem must be analogous to or similar to the problem stated by the words. So what we're learning here with these different reasoning processes, these apply not just to mathematics. Most importantly, they apply to a biblical worldview. Let's think of some examples here. Induction. Romans 1:20. Just look at that verse. Since the creation of the world, God's invisible qualities have been clearly seen, so that men are without excuse of knowing that there is a God. So they've been clearly seen. We can observe those things. God's invisible qualities, His divine power. That's about observation. That's induction. Deduction, that's real easy. Any of God's commands, whether it's the 10 Commandments, any of those. Those are rules. We didn't have to use induction to make them. God just gave those to us. He skipped inductive reasoning. He doesn't have to do that. That's just something that we do. Remember, deduction is application of rules, so we apply God's commands. God doesn't explain every single detail of our lives in the Bible, but we can apply the truths that are there to find out what His will is for us and whether we're doing what is right or what is wrong. And a good example of an analogy in the Bible are Jesus' parables. In Jesus' parables, He uses concrete examples to reveal some kind of truth, an abstract truth. An abstract, the word abstract means it applies to a lot of different situations, basically. So an abstract truth would apply in a lot of different situations. In Jesus' parables, He would use concrete examples or things that we could relate to in everyday life, and those revealed an abstract truth about something. You may not think this is necessary to go over all of this, but from a Christian worldview, I think it's the most important thing, is to see the connection between what you're learning in math and how that connects to a biblical worldview. Otherwise, really, what is the point of learning it? Just so that you can pass the SAT test or whatever? That's a good reason, but ultimately, just slow down a little bit and understand that all of this ties back to God and the way He has created us. He wants us to think using induction, deduction, and analogy. These mathematical ideas that we have here, the mathematical relationships and rules that man has created, we can use these to help us understand how to think correctly and apply that to help us understand how God has set up the Bible to help us learn about Him. Let's go on to part B now and talk about logic. In their study of logic, and in particular deductive reasoning, finding new truths given original truths, the Greeks used something called a syllogism in their investigation of deductive reasoning. Now, this deductive reasoning process that is designed to lead to new truths, it has a major premise, a minor premise, and a conclusion to it. The major premise, basically what that does is identifies a property of a certain set of things, whether it's people or animals or algebraic equations, just whatever it is. A minor premise, that identifies a member of the set. And then the conclusion is that the member has that property. That would be what's called a valid argument. Here's an example of a syllogism. The major premise is all cats are orange. The minor premise is that socks is a cat. So the major premise identifies a property of the set of cats, that they are all orange. And the minor premise identifies a member of the set, socks. So the conclusion is that the member, socks, has that property of being orange. So our conclusion would be socks is orange. That's what you would call a valid argument. Now, think about this. In the deductive reasoning process, it's the method of applying a rule. So here, our rule was that all cats are orange. So that was our beginning truth or rule. And let's put truth in parentheses here, because that's not really true. All cats are not orange. But for the reason, or for using an argument, for doing a logical argument, that's our major premise. Socks is a cat. Conclusion, socks is orange. That syllogism there would be considered a valid argument because it follows the deductive reasoning process. In a syllogism, for it to be considered a valid argument, the truth or falsity of it is not considered. It's just, well, does it follow that pattern of a syllogism, the major premise, minor premise, conclusion? Is the argument valid or not? Yes, that's a valid argument. No, that's not a true initial statement there. The major premise is not true. And that's the whole thing, is that all major premises in mathematics, those are all made by man. Man is subject to error, so you have to be careful. Like saying evolution is true as your major premise. That's not really a true statement, because evolution, it depends on what you're talking about there. If you're talking about microevolution, which is different breeds of animals and things like that, then yeah, that's true. If you're talking about a tree frog turning into a bat or something like that, then no, that's not true. It's never been proven. All deductive reasoning done by man is based on rules that were induced by man or observed. Man made observations to come up with these rules. Man can observe things incorrectly, though. Now, back to a syllogism, the three parts, the major premise, minor premise, and conclusion. Another way to think about it, instead of writing it out like that in that syllogism form, to determine if it's a valid argument or not, you can do something called an Euler diagram. Our friend Leonard Euler that we talked about before, he's always coming up with simplified ways of thinking about things. When you're doing a syllogism, you're talking about sets of things. So first we can talk about the set of cats. Socks is a cat, so Socks is a member of that set. As long as Socks is a member of that set, and we can draw that using an Euler diagram with circles to represent the different sets, and Socks is within that set, then our conclusion is valid, our argument is valid. Now, if our minor premise was that Socks is a dog, Socks would have been out here. He wouldn't have been inside the set of cats, and therefore our argument would not be valid. We could not conclude that Socks is orange if the minor premise was that Socks is a dog instead of Socks is a cat. Let's do a couple of practice problems dealing with syllogisms, and you can pause the CD and try to figure these out if you want to on your own. All I want you to do is tell me if that argument there is a valid argument or an invalid argument. Well, why don't we use our Euler diagrams to help us solve these problems. Take the major premise of A, all dogs have 3 legs. That's our big circle, we can think of that. And we'll call that the set of dogs. All dogs have 3 legs. Max is a dog, so Max is inside this Euler diagram. Our conclusion is that Max has 3 legs, so that would be a valid argument there. Even though that's not true, the argument is valid. We know that all dogs don't have 3 legs, but the logical argument there, the pattern, is a valid argument. So we would say that that is valid. Look at B. All rockets go into space. Challenger went into space. Challenger is a rocket. Let's use our Euler diagram first. Make a big circle that represents all of the rockets. And then it says that Challenger went into space. It doesn't tell us if Challenger is a rocket, though. So Challenger could be, I'll just put C with a question mark, or maybe this is Challenger over here. The conclusion that Challenger is a rocket is invalid. That makes the whole argument invalid. How could you make that argument valid? Well, you could make that argument valid in a lot of syllogisms. You can do this by switching the minor premise and the conclusion around. We could switch those two around. All rockets go into space. Challenger is a rocket, so that would tell us that Challenger was a member of all the rockets. Since they all go into space, that would mean that Challenger went into space. So a syllogism is supposed to help us understand that deductive reasoning process. And most importantly, it should help you see that if you have an invalid major premise, or if you start with something that's not really true, you end up with a conclusion that's not true either. And so deductive reasoning is supposed to lead to new truths. It could lead to new falses if the major premise is false. I think that's the whole theory of macroevolution is based on that. It's based on mainly the deductive reasoning process because we haven't been able to observe. We cannot observe what happened supposedly, what they say is millions of years ago, what some scientists say is millions of years ago or billions. Induction is the process of finding a rule through observation. Deduction is the process of using that rule. Observation or induction was skipped in this process of studying especially macroevolution, the one that we cannot observe. And that is why most of the things dealing with macroevolution are not true. And for sure cannot be proven to be true. Let's go on to part C now and study something called a contrapositive. Basically what a contrapositive is the opposite of the major premise, an opposite statement dealing with the major premise that is also true. Contra means opposite or against, positive, so it's like the negative statement. Let's use our major premise from practice problem A as an example here. All dogs have 3 legs. We can write this as something called an if-then statement as well. Look at this. We've changed it to say if an animal is a dog, then it has 3 legs. We call the if part of that statement the hypothesis. In science, a hypothesis means an educated guess. The second part we call the conclusion. Don't get that confused with the conclusion of a syllogism. So the hypothesis part, we're not saying that it is a dog, we're just saying that if an animal is a dog. So that's our hypothesis about that animal. We're guessing there. It's not a totally confirmed statement. But if it is a dog, then it has 3 legs. Let's use an Euler diagram just to look at that statement there. If an animal is a dog, then it has 3 legs. So we'll have a circle representing things with 3 legs. And a dog would be inside that set of 3-legged animals. Because if an animal is a dog, then it's inside that set of all the animals that have 3 legs. We could do a set outside of this as well. And we could, the animals inside that first circle are 3-legged animals. So outside of that would then therefore just be non-3 legs or non-3-legged animals. Animals that don't have 3 legs would be outside that set. So look at what I have written there. If an animal does not have 3 legs, then it is not a dog. That's the contrapositive. See, what we did was we switched the hypothesis and conclusion and negated them, made them not statements. If an animal does not have 3 legs, that conclusion became the hypothesis. Then it is not a dog. And we can look at our Euler diagram and see how that works. Animals that don't have 3 legs, those are outside the set that we're considering here. And this is a little bit better way to represent this in terms of Euler diagrams. We have a set of animals with 3 legs, and if an animal is a dog, then it is considered a member of that set. Then we have this other set of animals that don't have 3 legs. Dogs are not in that. They're in the set with 3 legs. So if an animal does not have 3 legs, it's not a dog. Let's solve a syllogism using the contrapositive method here. Look at this one. It says if the car is not moving, then the brakes are being applied. The minor premise is the car is moving. Therefore, the brakes are not being applied. Well, just think about it. Switch that major premise around. Let's just think about it in our head. If the car, or if the brakes are not being applied, then the car is moving. If the brakes are not being applied, then the car is moving. So we have this set of moving objects. And within that set, we have the group where the brakes are not being applied. So I'll just say no B for brakes in there. The car is moving, therefore it's a member of that set where the brakes are not being applied. Think about it this way too. We could have another set of the non-movers. I'll just say non-M for non-movers. We have a moving set and a non-moving set. No brakes being applied, only is included in the set of moving vehicles. So therefore we could say that this is a valid argument. We use the contrapositive to help us. If the brakes are not being applied, if there's no brakes, then the car is moving. Let's do one more. All dogs have 4 legs. Rufus does not have 4 legs. Conclusion, Rufus is a cat. Is that a valid or invalid argument there? Well, let's use our contrapositive to help us understand this. And remember, we can always make the major premise into an if-then statement. We could just say, if dog, then you put an arrow and you say then 4 legs. Think about the contrapositive to that. If non-dog, we could say. And we switch the conclusion and hypothesis around, so we would say if non-4-legged, then not a dog. So let's use that as our major premise. If not 4-legged, then not a dog. So if it's not 4-legged, then it's not a dog. That's our statement of truth. We don't worry about like just realistic things when we do these. That's one thing that can be confusing sometimes. You just worry about what you're concerned with there. Is that a valid argument or not? If it's not 4-legged, then it's not a dog. Well, Rufus is not 4-legged. He does not have 4 legs. Conclusion should be Rufus is not a dog. Not Rufus is a cat. That doesn't mean Rufus has to be a cat. It could be something else. So our syllogism then, the argument that it contains is invalid. If we said that Rufus is not a dog, that would have made it valid. Let's look at some more logical statements. They're called converse and inverse statements, and they're based on just dealing with the major premise, the if-then statement, the hypothesis conclusion component. The if statement is sometimes abbreviated with the letter P, and then the then statement with a Q. So we can just think of it just in terms of variables like that, PQ. In other words, if P, then Q is kind of what we're saying there. The converse, what that is, that means that this is also true. If Q, then P. The inverse is basically the negation or the opposite. So sometimes we use that little tilde mark or a minus sign sometimes to say if not P, then not Q. We call statements that have the major premise, the converse and the inverse of that major premise, if all of those are true, we call those if and only if statements. Here's an example. Let's use a right angle as an example. So we can say if the measure of the angle is 90 degrees, we could just call it angle x. Measure of angle x equals 90 degrees, then x is a right angle. If the measure of angle x is 90 degrees, then x is a right angle. The converse of that is also true. If, I'll just say RA for right angle, then it's 90 degrees, then the angle is 90 degrees. And the inverse is also true. If not 90 degrees, then not a right angle. Those are sometimes called if and only if statements. So when the converse and inverse are also true, and we sometimes represent those as IFF when we're dealing with logic. If and only if. And we would say P, and we use like a double arrow kind of going both ways to represent that the converse and the inverse are true. Notice this is not talking about the contrapositive, but the contrapositive would also be true. If not a right angle, then it's not 90 degrees. If and only if statements are used in logic, in the study of logic. Mainly what you'll be working with on your homework sets and your tests are the syllogisms and applying the contrapositive as needed to help you determine if they are valid or invalid arguments. Okay, well that's all for lesson 7.